Hi everyone, welcome to Chapter 8. In this section, you will learn how to write out chemical reactions, balance chemical reactions, identify various reaction types, and predict the products of reactions. So we already know that the chemical reaction, we're going to take our reactants and we're going to create the products. You can have one, two, or more reactants to produce one, two, or more products. We're going to be looking at balancing reactions today, looking at how the formulas are written, the subscripts that we are using to then create a balanced equation to obey the law of conservation of mass. You're going to be using what's called a coefficient. These are the larger numbers in front of something like you would have in math class, say 2 times x. It's a big 2 times the x. And that 2 would go to everything in that math, in the parentheses in math. So how do you know if a chemical reaction is taking place? You've seen something like this before in the lab. What you're seeing there is a creation of what's called a precipitate. You have two clear solutions producing that yellow color substance, and that will fall to the bottom as a solid. So the first thing we can see is there a color change taking place? Is there any exchange of heat? Do we have a change in the temperature of the reaction? It could be an endothermic or an exothermic. Now, those are not going to necessarily be large changes in the heat content. It might be very slight and maybe not noticeable. Are you seeing any bubbles produced? And again, here's that word precipitate again. Are you creating a precipitate from two aqueous solutions? In a chemical reaction, there are a lot of different symbols that can be used. We're going to use a plus sign to separate either two or more reactants or two or more products. Between the reactants and the products, you'll see what's called the yield sign or an arrow. If a reaction is considered to be what's called reversible, then you'll see a double arrow. If you produce a precipitate, there's two ways that you can show that. A precipitate would be that solid falling to the bottom. So we can use the symbol S, or since it is a solid falling to the bottom, you can show a down arrow. If something is liquid, and that would be water, we would designate that with an L. If something is dissolved in water, we would use the symbol AQ. It's creating what's called an aqueous solution. A lot of what you've used in the lab before have been aqueous solutions. If something is a gas, we can use the symbol G in parentheses next to the substance. And since gases rise, we can use an up arrow to also represent a gas. There might be some sort of heat that needs to be supplied to the reaction to take place. That delta sign is for change in heat. Maybe there's some sort of catalyst that needs to be considered. A certain pressure, you would put that above the arrow. You can see that again here. Maybe the reaction will only occur at a certain temperature. And maybe you need a catalyst. Now, when you learn the formula for photosynthesis, you may have seen the sunlight above the arrow. That means it's not used up by the reaction, but it's needed for the reaction to take place. We don't use up the sunlight. The sun's energy is needed to carry out the electron transport in the light reactions of photosynthesis. So you would see that as a catalyst. And you can see here some of the ways that those symbols might be used in chemical reactions. Here we have a certain temperature and that there's a catalyst that's needed. Here you see a reversible reaction. And in this one, you'll see the AQs and S's, which means that we took crystals of calcium bromide and dissolved them in water. Same thing with the silver nitrate. We took crystals of silver nitrate and dissolved them in water. And then as a product, you see this S. That means that silver bromide is not able to dissolve in the water. And just like this is not silver bromide. However, in this picture, you see that precipitate, and that's what this would be. This shows that we have a precipitate, and if this reaction were carried out, then what would be falling to the bottom of the beaker would be the silver bromide. So you already know that you can't, once you write a chemical formula, you don't change those subscripts because it's going to change what the substance is. So you're never ever going to change the subscripts once you write a reaction properly. And we're going to use what's called coefficients. And you can see those two coefficients in front of the hydrogen and in front of the water in the production of water from hydrogen and oxygen. That is a balanced chemical reaction where what you have on the left side of the reactants is equal to what you have on the product side. Now that 2 in front of the hydrogen goes to the whole hydrogen. That makes 4 hydrogen on the left side. We have 2 oxygen on the left side. If you look at the 2 in front of the water, it goes to the whole water molecule. So 2 times 2 for hydrogen is 4 hydrogen, and 2 times the 1 for the oxygen gives us 2 oxygen. That is a balanced chemical reaction. So in this picture, you'll notice that we're starting off with a certain number of element X, which is the white one, and a certain number of element Y, which is the red one. And in our product, we will have the exact same numbers of atoms that we started with. Remember, that's called the law of conservation of mass. The atoms that you start with are the same number of atoms that you end with. Matter cannot be created or destroyed. It's simply converted to another form. You don't have a place in your notes for these equations. Just read through them. We're going to look at representing a chemical reaction by showing the correct formulas for the reactants and products, and then we're going to balance those. Before it's balanced, it's called a skeletal equation. It's just showing the reactants and the products. It might not be balanced yet. That's a skeletal. However, sometimes a skeletal equation can be a balanced equation. When we balance equations, we want the simplest whole number ratio. You may or may not need to include the phase of the reactants and products, but you will need to understand what those symbols mean. And then I already mentioned this word today, something that speeds up a reaction or is used to get the reaction started, but is not actually used up in the reaction. And that's called a catalyst. Okay, so what we're looking at are the subscripts first. So in this formula, we have 2 hydrogens and 1 oxygen. We're going to use coefficients, which are those big numbers placed in front of them. You can see a 2 in front of the hydrogen and a 2 in front of the water. And that's going to balance it out. And look at the picture. That 2 in front of the hydrogen now gives us 4 hydrogen on the left side. We have 2 oxygens on the left side. The 2 in front of the water gives us a total of 4 hydrogens on the right side and 2 oxygens on the right side. So our number of atoms on the reactant side equals the number of reactants on the product side. And our goal is to use that law of conservation of mass and our coefficients to have a balanced chemical equation. Balancing equations is more like a puzzle. Kind of have to go back and forth. Once you get the hang of them, they're actually kind of fun. I enjoy them. So you want to make sure that what you have on the left side, the reactants, is equal to the number of atoms on the right side, the products. So in this case, on the reactant side, we have 2 nitrogen and 2 hydrogen. On the product side, we have 1 nitrogen and 3 hydrogens. So I'm going to start with the hydrogens. We have 2 here, and we have 3 here. What is a multiple of 2 and 3? The goal is to balance those on each side. So a multiple of 2 and 3 is a total of 6. So what can I put in front of the hydrogen to give me 6? Well, I can put a 3. So 3 times 2 is 6. What can I put in front of the NH3 to give me a total of 6 hydrogen? I can put a 2. So now I have my hydrogens balanced. But what did that do to the nitrogen? Well, that 2 also goes to the nitrogen as well. And then we have to go back to the other side and say that, oh, look, we do have 2 nitrogens. So if I asked you for the coefficients for this particular balanced equation, you would say a 1, but you wouldn't write it. It's a 1, a 3, and a 2. It's the mole ratio. Let's take a look at the next one. Notice that the potassium and chlorine on the left side is equal to the potassium and chlorine on the right side, so let's start with the oxygen. We have 3 oxygen here and 2 oxygen here. We need, again, to look at a multiple of 3 and 2. And again, that would be 6. So we can put a 3 in front of the O2 on the product side to give us 6 oxygen. And we could put a 2 in front of the KClO3 on the reactant side, again, to give us a total of 6 oxygen. But now what did that do to the potassium? What did that do to the chlorine? Now, we now have 2 chlorine and 2 potassium on the reactant side. So we need to make sure that we have 2 on the other side. So we're going to put a 2 in front of the KCl. And now our coefficients for this balanced equation are 2, 2, and 3. Now the next one, you can see hydrogens in several places on the left side, oxygens in several places on the left side, same thing with the right side. So you have to figure out, where am I even going to start on this particular one? If you think that you might be a little overwhelmed as to where to start, here's a suggestion for you. Let's figure out what atoms we have on the left side of the yield sign, or the reactant side, and what atoms we have on the right side. You have to have the same type of atoms on both sides. So I see a hydrogen, I see nitrogen, I see oxygen, I see sodium, and I see carbon on this side. I also see those same exact atoms on the other side. Now, I drew that line down underneath the yield sign so you can focus only on the atoms on the reactant side, or the left side of the yield sign. Add up your hydrogens. I see hydrogen in 2 places. That gives me 2. I see nitrogen in 1 place. I see oxygen in 2 places. I see sodium in 1 place, and I see carbon in 1 place. So when I combine those all together, I have 2 hydrogens, 1 nitrogen, 6 total oxygens, 1 sodium, and 1 carbon. Now let's look at the other side. I see 1 sodium, I see 1 nitrogen, I see a 3 oxygen, and then 1 more, and then 2 more, so that's a total of 6. I see 2 hydrogens and 1 carbon. So notice that the numbers of my atoms on my left side, or the reactant side, is equal to the number of atoms on my right side, or the product side. So in this case, we already have a balanced equation. This is a skeletal equation. That is also the balanced equation. Again, you would tell me, if I asked you for the coefficients, a 1, 1, 1, 1, 1. However, you would not write the ones in. They're understood to be there. Now, in the next one, notice what we have. We have a polyatomic ion on both sides. If you have the polyatomic ion on both sides of the equation, you can look at that as an entire grouping. So we're going to start with our polyatomic ion first. I have a sulfate ion right here, and I have the sulfate ion over here. Now, in this case, that 3 outside belongs to the entire sulfate. So that means I have 3 total sulfate ions. So what do I need to put in front of my potassium sulfate in order to get 3 sulfates? I need to put a 3. Now my sulfates are balanced. But what did that do to my potassium? Well, 3 times 2 is 6. So what am I going to have to put in front of the potassium bromide? I'm going to have to put a 6. So now my potassiums are balanced. That also changes the bromine. So what do I need to do to the bromine? Well, it's 6 now. I need to do something over here to give me 6 bromines. Well, I have 3 already, so 3 times 2 would give me 6. But now that changed my aluminum on the left side to 2. So I need to go back over to the right side and look at my aluminums. And that is 2. So this is a balanced equation with the coefficients 2, 3, 6, 1. This one also has polyatomic ions. I see nitrate on both sides. I see the nitrate there in silver nitrate. And I also see it in the copper 2 nitrate. That 2 outside of the nitrate means that that 2 goes to the entire grouping of the nitrate ion. So we have 2 of those groupings. So over here, I need 2 groupings also. So I'm going to put a 2 in front of the silver nitrate, which then gives me 2 silvers. So on the right side, I need to put a 2 in front of the silver. Now my silvers are balanced, my nitrates are balanced. The last thing I need to check are my coppers. I have 1 copper on the left side of the yield sign, and I have 1 copper on the right side. So now this is a balanced equation. The coefficients are 2, 1, 1, 2. The next one, I see that I have 2 aluminums on the right side, 1 on the left side, 3 oxygens on the right side, and 2 on the left side. I'm going to take a guess and start with the oxygens. Again, we've seen this before. What is the multiple of 3 and 2? 6. So we're going to create 6 oxygens on the left side by putting a 3 outside of it. And we need 6 oxygens on the right side, so we'll put a 2. Now notice what happened here. What does that do to the aluminum? Well, it now makes 4 aluminum, so we're going to put a 4 over here. So the coefficients for this balanced equation are 4, 3, and 2. The last example has 2 polyatomic ions. So we are still going to start with a polyatomic ion. I see sulfate in 2 places, and I see acetate in 2 places. Now notice with the sulfate, the cation, you have multiple cations. You have 2 irons with the first sulfate, and you have 2 sodiums with the second sulfate. With the acetates, you only have 1 sodium and 1 iron. So we're going to start with the sulfate. So let's start with the sulfate. Again, keeping in mind that 3 outside pertains to the entire sulfate. So we need to have 3 on the other side. So we're going to put a 3 outside of the sodium sulfate, which changes my sodium to a total of 6. So I need to put a 6 on the other side. So to get 6 sodium, we're going to put a 6 in front of it. Now notice what that does. Remember, this is a polyatomic ion. We still can look at this as an entire grouping. That gives me 6 of that entire grouping. Now let's go to the other side. There is my acetate ion, and I have 3 of that entire grouping. So I need a total of 6 on this right side. So what needs to go there in order to give me 6? Well, that needs to be 2. 2 times 3 is a total of 6. Then I now have 2 iron on the right side. So I need 2 iron on the left side. Let's check the iron. And it is 2. So we now have a balanced equation with the ratio of 6 to 1 to 3 to 2. All right, folks, thanks for listening.